Well, good morning, class. Good morning, teacher. I'm Randal Schwartz. I'll be your tour guide for the next hour and 45 or 50 minutes on my wild, quick introduction to Git. Let's just put it that way. There's this conference, there's this a phenomenon known as conference crud, where you go to a conference and you pick up some head cold or other disease, or just generally feeling bad because you're around a bunch of people you're not normally around, and that you always get it from some guy who must have brought it with him. I am the guy this week, sorry. I came in with a head cold, and so if I have to sneeze or cough sometime during this morning, I apologize in advance. I actually got almost no sleep last night. I kept waking up coughing and sneezing, so I'll stay way away from y'all, don't worry. I'll try not to breathe on you, but I may have to take care of biological things up here occasionally, so we'll just go with that. Everybody hear me okay? Good. It's a really nice system, actually. I wish I had this in more places. It's really cool. So a little about me, talking about, that's the only fancy transition in there. That's pretty cool. All right. So I've been tracking Git since it was created. It turns out that Linus Torvalds, who created Git, moved to Portland, my hometown, in 2007. And to introduce him to the town, I bought him a microbrew beer at the local beer place. And I said, what are you working on these days? He says, well, you know, the Linux kernel. And I said, I figured that. And he goes, but I'm also been creating this change control system because we had to replace BitKeeper. And so I said, well, I'll check that out. And I downloaded it, had a great time with it. And I've been with the project essentially ever since. I've been sort of the canary in the coal mine for compiling Git on non-Linux operating systems for at least the first couple of years. I've used Git on small projects. I've used other systems on small and large projects. I have a long history with both good and bad change control systems. And I've read a lot about people talking about Git on the mailing list. And I've actually provided some patches to Git and suggestions for the user interface changes. So I've actually been involved at that level too. And I've worked on small and medium teams at Git, but not large ones yet. So I do have some limited experience with this. I'm watching what other people do, but I'm not really that guy. So let's talk about Git. So what Git does is it manages changes to a tree of files over time. And I say it that way because I want to distinguish Git from some of the other change control systems that are looking at individual file history. Git does not track individual files. It tracks the tree of files. This actually affects the way you think about Git and think about patches and changes that Git creates. Git's optimized for distributed development. That's really sort of the main thing that created these distributed version control systems like Git and Bazaar and Mercurial and things like that. It's also optimized for huge file counts. Originally created for the Linux kernel, which has something like 30,000 files in the file tree. You got to be able to do things quickly over a 30,000 file tree. A lot of you are probably using Git or will be using Git on projects that have 100 files, but trying to do that over 30,000 files means there has to be certain optimizations in there. It's also optimized for complex merges. When you have something as complex as the Linux kernel and you have distributed development on that, people do different things in different repos, so you have to be able to pull that back together and do it quickly. So Git is optimized for that sort of thing. It's also optimized for just trying things out. This is probably my favorite feature. One of my favorite features of Git is that I can go ahead in my local repo and say, well, what if I take the code this direction? And then I could try 4 or 5 commits on my way over there, and then I can go, oh, this really didn't work, and completely erase it, and nobody will know. It's not like a central control system where you're either afraid to check it in because you don't want everybody to see your bad work, or you have all the local files that are like, foo.c.good, foo.c.previous. I mean, at that point, you've lost the whole point of a change control system because you can't check it in somewhere. You can't commit on your path towards either greatness or total failure. You want to be able to have commits all the way down one way or the other. It's also optimized for being very, very fast. The code that's in there is incredibly slick and fast. It's also optimized for being robust. Git's very, very, very careful to not lose anything that you've done. There are sequences of steps that it makes sure that this file's first in the object tree before it brings it back out to the work tree and so on. So a lot of things behind that. It's not optimized for tracking file permissions and ownership. In Linus's words, Git is a source code manager. So it doesn't have any information about meta stuff, like who owns the file, what permissions it has. It doesn't care about that stuff because source code doesn't matter there. And what would it mean to merge a tree together where I own some of the files and you own the other files? I mean, it would not make any sense. So Git just says, here's a chunk of text or a chunk of binary, and that's all you've got. It's also not optimized for tracking individual files with separate history. So one of the things that people tend to want to use Git for. I don't quite know why, but it's like to manage their home directory. You know, and the problem with that is really you have no correlated change between your vimrc file and your SSH config file. There's no real correlation between those changes, and yet you're telling Git, correlate these. And it won't make any sense to Git. Also, you're probably not branching and merging your home directory. So that's another reason not to use Git for that. And it's also not optimized for making things painful. Okay, so other systems seem to be doing that. Okay, so why Git? Well, it was essential to Linux kernel development. That's where it all got started. It was created as a replacement when BitKeeper suddenly became unavailable. So for a long time, the Linux kernel development was just simply Linus taking patches from people and applying it to his own personal tree, and then publishing that tree from time to time in whatever repo he did that. But obviously, as Linux grew in terms of development, the more people were working on it, it got more and more complex. So they made a deal with the people that made BitKeeper to actually provide a distributed version control system for them as a free license. BitKeeper is not open source software, but they got a license that was essentially free for all the developers. Well, somebody screwed up with that, and they couldn't use it anymore because, long story. Anyway, so all of a sudden they're left with no change control system that works again, except Linus accepting patches back to his original tree. So he's trying to figure out how to make that work. So he created it sort of within about a month. He actually created a working version that was able to manage itself. And of course, now that was 2007, so we've had quite a lot of development on it since. It's now used by thousands of projects, tens of thousands of projects. I mean, take a look at everything that's on GitHub, for example. Lots and lots of people are using this stuff. And one of the things is that in open source projects, if you're using a central control system, you have to sort of display your worth before you can get a commit bid. In other words, be able to generate patches and commit those in a way that other people can see your work. With Git, everybody has a commit bid because I can take your repo, fork it to be my repo, and then I can make changes to it. And you may or may not want to take my changes back, but at least I can go ahead and show a history of the things I want to add to this project that's now forked. So because of that, everybody can clone the tree, make and test the local changes, submit the changes either like as patches via email, that's possible, or you can submit them as a published repository. In other words, I can clone your repo and put it up on GitHub or something and then say, okay, here's my changes. And the great thing about Git is that even if you've made changes since then, Git will know what the common ancestor is to be able to do the merges or the rebasing all automatically for you. And so again, I can also in my repo track the upstream. So I can look at your repo as you're making changes and pull them into my repo in a way that makes sense. In other words, I can actually keep applying my changes on top of your changes as you keep updating things and moving them forward. So how does it do it? It does it by using universal public identifiers. We'll talk more about that in a minute, basically the SHA-1s of the various things. None of this, my 245 is your 992 and stuff. That always confused me when there's two different possible numbers for the same actual commit, depending on which repo and what path you took to get there. It's also good because it transfers over multiple protocols. We'll talk more about that in a few minutes. You can pull down a Git repo via HTTP or via SSH. There's your own Git protocol as well. It stores objects efficiently. So because everyone has the entire repo. Now let's talk about that in practical terms. The entire history of the Linux 2.6 kernel since Git was installed all the way up to the 3.0 kernel now, is the entire history for that. Every single commit, every single change in a Git repo is about half the size of the current checkout. So in other words, it's like a really, really super compressed tarball, but it's better than a tarball because it's the entire history with all the commits and everything in it. When the X11 guys also went over to use Git, they found that every commit in history that they had about X386 would actually fit in a repo that's only 3 times the size of the current checkout. Every commit from all the way back to the beginning of X11. That's really awesome. So the repo size is tiny, and it does this by doing lots and lots of optimizations. We'll talk more about that as we get further on. Okay, easy branching and merging. So when you have a project where multiple people are working on it, you're always going to be having different diverging work. People are doing different commits in different directions. And one of the things that's essential then when you're doing distributed development is you have to be able to come back to a common place, come back and merge your work in with my work in. And the trickiest part of this is if a file gets changed in 2 different directions, in 2 different people's commit streams, you have to know what the common ancestor is to figure out what I did versus what you did. That's the only way to do it, because if you just have two files and they're different, you don't know how to merge it, because just, well, this is different and this is different. But by having a common ancestor, you can see that I added lines 1 through 10 up here, and you added lines 20 through 50 over there. So then we know what the common ancestor is. We can compute the merge calculation. And this is a lot of what Git is all about, always being able to know where the common ancestor is, to be able to do these merges, to bring the work back together. So it's very, very calculated that way. Another thing is that Git tools were designed from the beginning to be able to do patches through email. So there are a lot of people working Linux kernel, but there's only about a dozen lieutenants that actually have sort of an actual Git repo that Linus pulls from. So everybody else sort of downstream of that sends patches by using Git tools that specifically put the email in a way that the person who's incorporating that will know exactly what particular commit this is being applied to. So it makes it real easy to be able to pull that in and then merge that in and so on. It's really nice that way. Git also does support binary files to a limited degree. Since Git's a source code management system, it doesn't know things like how to merge binary files. So you're not going to be very happy if, say, for example, you're managing open office files with Git. That's not going to be very cool for you. It's not going to like merge lines of text for you. It's just going to say, here's a blob, and it's different from this blob. Too bad. That's all it's going to say for you. Now, one of the secrets behind all this is the use of a hash called SHA-1. You're going to see a lot of references to SHA all the way through the entire presentation here. Every object, every file, every tree of files, every commit has a SHA-1 that uniquely identifies it. It's a 40-character hex string. So you'll see this is a lot of times in this demonstration here. So objects is everything in there. Blobs, which would be the content of a file, has a unique SHA-1. The trees, which represent directories of blobs and other trees recursively. So a given SHA-1 will identify completely and accurately every set of files that are below it. Also commits. So the commit consists of three parts. It consists of a tree plus 0 or more parent commits plus a message about why. So basically the commit message. I'm doing this, I'm changing this file because it needs this feature and so on. I'm fixing this bug, whatever. So another thing that SHA-1s are also used for is tags. We'll just step outside for that for a bit. A tag is an object, typically a commit, with an optional subject saying why we're tagging this thing, plus an optional payload to sign it off. So that could be, for example, maybe a GPG signed message or whatever. Yeah, sorry, that's the next piece there. And a tag is basically used when you want to say this particular commit is version 1.4 of my software. So it's basically where you lock down a particular commit and publish it publicly to say, this is a special commit, it's more special than most, and that it actually represents a release or a preliminary release or something like that. So it's basically designed to be mobile, not changing around. And so how we start with these things is we're going to put objects, basically your files and stuff, in a repo. So Git efficiently creates new objects, does this in the repo, and it does it in a way that it doesn't have to lock the repo when multiple people are all pushing things in. It generally adds objects rather than destroying objects. Only in a few rare circumstances does Git go through and clean up the object tree when you tell it to be able to garbage collect and so on. So what's great about that is that if you have a Git repo on a central server and everybody's pushing more data into it, it's just adding objects. So there's no locking required for that. It's very efficient that way. Eventually unreferenced objects do garbage collect, but objects actually, when they're first put into the repo, are a file of their own. So every new thing that's being loaded in is loaded in separately as a file of its own. But eventually, when you do garbage collection, it packs those into much more efficient things. And you can actually tell Git, please make this entire repo one giant file, so it's efficient for putting on a tarball or sending somewhere else. So the packs are actually smart, because when it puts something in a pack, it looks at parts of files and sees if there's a way to make this the second file being the same as the first file except for these bytes. And in those packs, looking for those deltas, it can actually be really efficient in compressing that. That's why the entire history of the Linux kernel fits in half the space of the current checkout, because there's a lot of all those files that look very similar. So those are actually compressed down using this packing system to be able to have the same thing in multiple places. Packs are also used for repo transfer, so when you're pulling down something from a central repo, pulling in just your new objects that you don't have yet, it actually, on the server side, it actually computes a new pack that's just the things that you need to have that are different. And so it does that very efficiently. So the transfer protocol is also very efficient as well. And commits is what drives everything. Commits traps what we do. It tracks what we do. So basically, the heads of the various branches of development are a commit. So one or more commits, that's the head of all the object chains that lead back. There's typically one head called master. So when you first create a Git repo, you'll get a new branch called master. There's nothing special about the 6 letters M-A-S-T-E-R. It just happens to be the name of the initial branch that you pull down. So what a head is there is that it's a commit reflecting the tree of files at your initial check-in. But I'll get to that in a minute. But you can make other branches at will. Okay, so you can just create whatever branch names you want. They're all local to your repo. They're not reflected in any central repo until you actually push them. Okay, there's typically one commit in the repo that has no parent commit. We call it the root commit. That's basically says, here's my initial tree setup, and we commit that. So from a commit, what a commit actually contains is it has as one element of it the SHA-1 of the tree of files that the commit represents. Now, Git can then use that SHA-1 to go into the object repo that it has and pull out first the top level directory, then recursively down all the subdirectories for that particular commit. But the commit then containing this SHA-1 for the tree of files means that Git can exactly precisely duplicate the actual set of files at that moment in time. Now, the commit also has, if it's a commit from a series of commits, also has a SHA-1 that points upstream and says, here's the parent commit. Here's the commit that happened before the commit I was. So we can chase down that part of a commit and figure out what the tree of files was as a parent, and so on. Just keep chasing that down recursively. We end up with everything all the way back to history. Okay. So the interesting thing about this is that since every commit has a hash of the tree SHA-1 plus the parent SHA-1s, we know that if we have this particular SHA-1, we know exactly and entirely the entire history back to the dawn of time for these particular commits. So a given unique signature can tell us the entire history, provided we have all the component objects in our repo. And this is one of the interesting things about Git. If you know the SHA-1 of a particular commit, you also automatically know the entire history of everything that got there. You can prove that this is the history for this particular set of files. So that's one of the interesting things about this, is it's sort of a cryptographically strong way of proving that I have the entire history and exactly the way it went. Of course, I think they've done some studies. SHA-1 is still not quite broken yet, but there's plans eventually to make it SHA, whatever the next one is, but SHA-1 is good for now. Seems to work. 40 characters seems to be plenty. So as a person using Git, I will have a working directory, a working tree. Now, the way this lays out on the disk is that I have a tree of all the files that I'm playing with, but at the very top level, there's a .git directory, and that belongs to Git. That's the thing where all the Git commands will go look for to put their stuff in and move things around in. And unlike CVS or SVN, CVS is a version, there's no pollution of deeper directories. So you don't have to write special tools to ignore the .svn directory in every one of the subdirectories. You don't have to write all that because there's only this .git right at the top, no problem. Really nice for recursive greps and so on. So what that contains is there's a config file in there. It's an INI style file with brackets and subsections and stuff. There are commands to manage that. It also contains the objects. And again, objects here are in the sense of blobs or commits or trees, objects and things like that. That's all going to be in there. Under refs heads, you'll see all the things, the branches we'll call them, things like master or upstream, wherever you want to call it for that. And that's just going to be a reference to a SHA-1 that says, here is my current master. It's this SHA-1. And it'll translate that then into the appropriate objects when it looks at it in the object tree. We also have the tags there. We have logs, various logs that happen through there. As you start making commits, Git is actually tracking for the previous 30 days where master has been, so you can always recover back to that later on. Very handy when you accidentally destroy master and you got to figure out how to get it back. And also remotes. So typically you're working with others. So the way that works is that underneath refs remotes, you'll have the name of a remote name like origin or some other names like that. And then below that, you'll have SHA-1s of what the remotes mean for those particular branches. So that's where the SHA-1s go for that. And then there's this magic index. We'll talk more about that later. This is basically the status of the next commit you're about to make. So in other words, you add things to the index to say, I'm about to commit these things, and then you finally do the commit based on the index. And then there's this magic one called capital head, and it's basically pointing to one of the branches. So for example, it will point to refs heads master when you're currently on the master branch. It might point to one of the remotes. It might actually be headless, where you actually point at just a commit name, and we'll talk a little bit about that later as well. So the key thing, oh, here goes my throat. Please, yeah, please.
So the objects are in one directory. All the SHA-1s are everywhere else.
Yeah.
How are they linked? Is that in the index?
No, that's the code links those. In other words, the code given a SHA-1 can go into the object tree, and based on the names of things in the object tree and the indexes that are inside there, it's able to extract objects. So there's the object tree is actually there's .idx files that are indexes, and it goes inside those, and those have mappings from SHA-1s to other longer object names and stuff. So yeah, that's a black box to me. It just works. All right, but that's all I care. As long as Linus knows how it works, that's all I care. All right. All right, so the index is, in logical sense, is a directory of blob objects. And it really just is there to represent the next commit. Unlike most change control systems where you basically spell out explicitly, I'm committing the entire tree, I'm committing everything in this directory or whatever, Git allows you to stage files, which means that you can say, I've made all these changes, but I really just want a commit that represents these 5 files because logically that's a change I want to record as a separate change. And so we'll see how those commands work in a few minutes, but basically you can say, okay, I start from my original commit, and I've made changes to 20 files, but I only want these 5 files to be part of the commit. And that is what you add to the index before you do the commit, and the commits are always made against the current index. So you're going to add files to put contents in there. I'll show you the syntax in a little bit. So commit, when you say finally git commit, it's going to take the current index, whatever's actually in there, and make that the next commit. And then everything moves forward. So the difference between head, which was the previous commit, and the index are changed things that are not yet committed. So head was the previous commit. Now we're adding things to the index. The difference between those two is what's going to get committed next when I say commit. The difference between the index and the working directory are things that I've changed but not yet added to the index. Now I have to say 99% of the time, you're just going to take everything you've changed, add it all to the index, and immediately then commit it. But there are times when you want to say, well, wait a second, the changes I made in these 5 files or these 10 files sort of make sense together as a separate commit, and maybe somebody just wants that feature rather than all the stuff. So the default processing for Git is to do everything, load it all in, but the fact that you can do this sort of staged edit makes it a little more interesting and a little more complex to describe. And again, this feature's there mostly because this is the way that Linus was working. He would have a commit that he would make, and then he'd be working, sort of pulling in a bunch of stuff, moving things around, but he'd only want to commit like part of it because that's the only part that's working so far. So that would be the way this would be working. So this feature's there because Linus needed it. In fact, almost everything that's in Git is because Linus needed it for the Linux kernel. Luckily, it happens to be a good workflow for almost everything else that's large. And also untrack things. So I can also tell Git, ignore these files over here. For example, .o files. You don't want to be checking in .o files from a C compilation. So you can tell Git, ignore all the .o files, ignore the files in the subdirectory because it's all output work and so on, or ignore them because they're configuration files or whatever. So the difference between the index and the working directory might also be the things that are untracked. All right. So one of the things that's interesting about Git is it does not actually record any explicit renaming. And it doesn't expect you to declare it either, because exact renaming can be determined by the SHA-1. If I take a file in this directory and move it over to that directory, it's going to have the same SHA-1 for its content. And Git can detect that by saying, oh, the numbers are the same. So I know that this is the same content as this over here, so that must have been a rename moving one to the other. If you ask Git nicely, it will also detect copy and paste edits by similarity. In other words, you can say this file is the same as this file, except these 3 lines changed. And you can use that knowledge when you're doing merges to actually apply the merge to the right place. Because the file being applied over here really should be applied over here. Git can detect that as well, if you tell it nicely. Okay. And computer's better than you at that. You know, it's going to keep track of all these SHA-1 precise renamings and all the similarity things, again, if you ask it nicely. Much better than me sort of remembering that while I'm doing my development work. So kind of nice that it takes care of that all for me. Because explicit tracking is going to be wrong sometimes. Linus was finding this with other systems where they made you explicitly record renames, is that occasionally that would actually make merges harder to do because people aren't as good as computers apparently. So it was a little bit of a problem. So being wrong breaks merges, so there's no reason to actually record that. So that's something also to kind of get over. There is a command that says git move foo to bar, but all it really does is does the explicit commands of actually really renaming foo to bar and then telling the get index ignore foo and telling the get index to add bar. But you can just type those in directly and it's exactly the same operation. In fact, you could take the contents of file foo and delete the file and create a brand new file called bar and add it, and that would be exactly the same operation. It's the content that matters, not the actual identity of the file. So that's the other thing that's interesting about Git is it's a content manager. It's not really a file manager. One of the other things that's interesting coming out of this is that Git does not track directories. It only tracks files. So people often ask, well, how do I add this empty directory to Git? You don't. There's no content in there, right? So Git's tracking content. There's no content in an empty directory. So you don't get to do that. Okay. So Git also speaks many protocols. I mentioned this a little bit earlier. You could just rsync a Git repo from one place to another, and it's perfectly valid once it arrives there. So basically the tree of files in .git, you can copy them around and it works just fine. There's also protocols that will speak HTTP if you have it on a website. Slight problems with that, but I'll just skip over that. The Git protocol to talk to a Git server is there, but primarily the way people actually transfer files back and forth in Git is with SSH. So, for example, when you set up a GitHub account, you're actually setting up a SSH public key connecting to them, and then they know which repos you actually have. And they actually make an SSH connection for every Git command that you specify, and it talks to a remote command that sits on the other end and does all the protocol on the other side. So I'd say 99% of the use of Git is over SSH at some point. Okay. You can also use Git with local files. So I could actually have just a local Git repo and manage my trees that way as well. So Git also has the ability to import and export with both CVS and SVN. So for example, I might use the CVS thing to have an entire history of a project when I'm flying along at 30,000 feet. So it's great. So I can bring in somebody who's using legacy change control systems. I can still have the entire Git repo to be able to manage that. I have to say though that using Git with either CVS or SVN is a bit like, people wanted that and people think that's the right way to go when they're using SVN. But for me, it's like the old example of flying cars. It's a flying car. It would be neither a very good plane or a very good car. Okay, but everybody wants it. Everybody wants a flying car, but then they forget it's not going to be a very good plane because it's also a car, and it's not going to be a very good car because it's also a plane. And Git with SVN or Git with CVS is the same problem. Everybody wants it. They want to be able to go back and forth, but it's not going to be really good at all. So try to stay, use it as maybe a temporary solution if that's what your organization is using like SVN. It does actually allow you to do some pretty nice things with Git on top of SVN or on top of CVS, but stay away from it if you can. Okay.
Any RCS support?
RCS. I don't know and I don't think so.
For CVS, it kind of has to have some RCS.
Yeah, there's probably some of that.
CVS is built on top of RCS.
Yes, that's a good point. Okay. So there are some third-party solutions for things like Perforce and all the other big guys, being able to import those, pull them all in, migration between Mercurial and Git, things like that. So there's a lot of things out there. The Git core actually has a CVS server in it. So you can actually have on top of your Git repo, you can provide a CVS interface. So you can kind of go the other direction too. You have all the cool people are using Git with this repo, but you got some legacy client that only speaks CVS. You can actually pull that in and out. I have not used that personally, and I hope never to have to use that personally. Okay. Because once you play with Git, it's kind of hard to do that. So you can get the latest Git by going to Google Code. There's also packages for all the existing existing Linux things. And you can also track the Git developer archive. You can clone that particular URL and you're actually tracking day by day, sometimes hour by hour changes to Git. I actually track this daily and I download Git, the latest Git, compile it, make sure it works on my laptop. As I said earlier, when I started the Git project, I was pulling it onto my OpenBSD system and onto my laptop, my OS X laptop here. And I started noticing problems because there was a lot of Linuxisms in the Git code. So I went on the mailing list and I said, do you mind if I point out these things? They said, no, we actually expect this to be on non-Linux systems eventually. So I've been the canary in the coal mine for a long time about compiling on non-Linux systems, since I don't run Linux anywhere. So I needed to have this to also work. And Linus knows I don't run Linux anywhere. Yeah, okay. So maintenance releases are very stable. So there is a branch on this tree that is sort of working its way towards the next release, and I found it to be completely usable every day. So I've never seen a problem with that. They're very good at having side branches that are sort of experimental process, experimental features going into it. Very good at that. So the maintenance release for these things are very stable. And I just put mine in opt-get, so I get it out of the way of everything else, and I add opt-get into my path. Late versions, recent versions of Git, I've seen that in the last 4 years, there's actually only one binary that has to be in your path, and that's the actual Git binary itself. It will go find where it's installed and get to all the other pieces of everything you've got. So it's actually quite nice about that. So let's look at some actual syntax, finally, yay. So enough concepts, let's look at some real command lines, okay. All the Git commands start with Git, okay. Now, in legacy Git some command bar has also been written as a one command, Git dash that command bar. And in fact, you can still type that in if you have that Git bin in your in your path. But Git now works, so basically ignore that second bullet, really everything's like that. But the man pages, the reason I'm talking about this other syntax where you say Git dash the command is that the man pages are still there. If you want to type man git something, it's man git dash and then the subcommand. Okay, so you have to know this convention about that. And a lot of the documentation still talks about it that way, where it says git dash commit as one command. But nowadays you just type git space commit. So that's the typical how you can invoke that. But you can avoid knowing this, and just completely forget everything I said in the last 30 seconds, by saying git help and then commit, git help commit or whatever. So you don't need to know that there's actually a command called git dash commit, but it's still in there, okay? Or you can type git commit dash dash help. Lots of different variations for that. So you may see occasionally as I'm referring to things, I might put the whole command with git dash whatever, but that's legacy stuff and I'm trying to get those out of these slides. Okay. So the other thing that's sort of consistent about the git subcommands is that they're divided into two categories, porcelain and plumbing. Plumbing is the low-level Git operations. So these are things that are really close to the metal, actually working on the actual repo, accessing various things about that. And the higher-level operations are called porcelain. Okay, so that is sort of more the user interface commands. So you'll see even on the main Git man page, they'll break the commands into two categories. In general, you're going to be typing the porcelain commands. Things like commit is a high-level command. Things like status is a high-level command. But there are low-level commands, and the reason is that both of them are included is that you're going to be using porcelain, the stuff that's got the nice pretty output from the command line. So that's the kind of stuff that's going to make sense to humans, right? It's going to have lots and lots of annotations and things like that. But they would be hard to parse if you're writing a script with it. So this is the reason for the two different categories, is that if you're going to write any kinds of scripts that actually drive Git to do different things, you should be using only plumbing. So make sure you're only using commands in the plumbing category. That means you're going to have to do a little bit more of the work, but there's actually not much semantic difference between the porcelain and the plumbing in terms of what it can output, but you have to do a little bit more work to parse the output of the plumbing. What's really nice for that is that the outputs of the plumbing is committed to be upward compatible. So you're going to write a script today against the current Git and write it based on the plumbing. Then 2 years from now, the script should still work. 6 years from now, who knows? But 2 years from now, the script should still work, and that's the whole point of that. The plumbing is also good because it has various options like -Z on a lot of them to be able to output file names that are null terminated rather than space terminated. And that's really, really important when you're writing scripts because you don't want somebody's space containing file name to screw up your script. Whereas the porcelain, of course, doesn't have that kind of option because you wouldn't want to put a null out to a human reader. They can't see the null and then it's all really messed up. So the porcelain commands tend not to have that kind of option for those. Okay, so how do we get from a collection of files to an actual Git repo? It's actually really simple. We cd into the top level directory and we type git init. At this point, Git looks at the current directory, makes sure there's not already a Git repo or that it's inside a repo already, and says, okay, cool. And it creates a .git in the current directory. So that means that we now have the object tree, the master branch, all that stuff is all created at that point. Okay, so we just cd to the top of our directory and say git init, and it's done. You can also cd to an empty directory, so that works too. Now, another thing you might want to do before you start using this is to edit the .gitignore file. The .gitignore takes typical file glob patterns like star.c, star.o, and will make sure that Git doesn't pay attention to those files in the directories from there below. You can have a gitignore in every directory that you want. It only applies to the files below it in the tree. I typically end up with just one of them at the top level directory, and I spell out the things in there that say that are the things I don't want to have. For example, I use Emacs, so I have typically I'll have star tilde in my .gitignore because Emacs is creating all these tilde files as the backup files. Whatever text editor you use, you probably want to create something in the .gitignore that ignores your particular text editor files. Now, once I've done that, I can tell Git that I want to pay attention to all the rest of the files from here down by doing git add dot. In this case, whatever I'm telling add, it's doing it recursively. Dot, of course, would mean recursively from the current directory on down. Now, this hasn't committed it yet. This is simply adding it to that index. I said earlier, the commit takes the current index and makes a commit out of it. So by saying git add dot, I'm saying take all the current files as they currently are, and this is what's going to be my next commit. And then git commit for that initial commit. That will fire up a text editor with the list of files being added and a place for you to edit a commit message. So you want to put something nice there. A good commit message has two parts to it. It has a brief description of what the commit is, typically under 60 or 70 characters as a line by its own, and then has a long description after that. Often don't do the second part because I'm lazy, but the first part is essential because when we're looking at logs, it generally just prints that first line. So you want that to be a really nice sort of summary of what the commit's about because that's what's going to end up in all the logs. So once I exit the text editor, Git says, okay, and it makes the commit. It takes the current tree, creates the SHA-1 from the tree recursively on down, and then creates the commit message, adds that to it, adds a date and timestamp, adds my name to it, and then creates the commit message from that. So now we have a new head. It'll be that particular head. Yeah.
The .gitignore, would it be tracked and it would be in the same directory as .git?
Yes, the .gitignore is also going to be added unless you tell it to ignore the gitignore, okay, which you can. Okay, but otherwise, yeah, it's going to add that too. There's actually another option. If the gitignore should really only be for things that everybody should ignore. But if you have, I sort of lied a bit earlier because I put star tilde in another file. It's called .git/config. Oh no, .git/info/exclude. Sorry, the /info/exclude file is just like a gitignore, but it's not tracked. It's not part of the repo. So it's good for me, but not other people. So that's pretty handy as well. But gitignore should be for things that everybody should ignore. Okay, like maybe the result of build products like .o files. If you've got a make file and then it's going to create .os, probably want to add gitignore to that so it doesn't mess people up when they go to their system as well. Okay, yeah, good question. So we do git commit. We've got the initial commit there. It's going to create an initial branch called master. Again, nothing special about the name master. It's just the default when you're coming out of the chute here. So that is going to create a commit, and the commit is going to be accessible by two different names. Capital head, which represents the current commit reflecting your working directory, and master, also reflecting the head of the master branch. Now, as we make more commits, master is going to keep moving forward in step with head, moving forward and forward and forward. But as we create other branches, then master will still reflect this old branch, and we can go back to it anytime we want to later. See more examples of that later. Now, we could also do this on a tarball. We could extract the tarball out, cd into it, git init, and git add dot. So we actually could take an initial tarball coming from somebody else and create that as our initial commit that we're going to be building work on. Okay? I haven't coughed too much. It's pretty good so far. All right, so moving on. So once I have a repo, if I want to work on it in two different places, or if I want to let you work on it as well as me working on it, we have to clone. So there's two ways to create a repo, git init and git clone. Okay, so with git clone is going to create a subdirectory, and your work files and your .git are in there. Same thing as before. It's basically git clone, remote spec, and it will create the local directory. I'll talk more about that in a second, show you the actual syntax. But your work files and your .git are in there. And an interesting thing about cloning is that, so I have a master branch in my repo. If I clone it over to your repo, and you create a brand new repo from there, you're going to have a remote that points with master back to my current master. So they both have the same SHA-1. We know that my master is the same as your master because they have the same number. and you have all the same object files that I have, so you can reconstruct that from the SHA-1 all the way down to the same tree. But of course, I'm going to have additional work going on, and that means your master is going to be out of sync with my master, and that's what all the resyncing stuff is I'll talk about in a few minutes. So also, if I have a head branch checked out, you're going to have that as your initial master branch as well. So I want to distinguish in this cloned repo, there's two kinds of branches over here now. There's the branches that are worked on locally, like master, and there's the branches that are tracking my branches over here. So we call those tracking branches versus local branches. And there's different ways of specifying that. I'll show you the commands in a few minutes. Because all other thing this does is that, again, by default, when I clone from my repo to your repo, or when you clone from my repo to your repo, it also sets up a remote called origin. Origin just says this is the thing I was initially cloned from. And there are commands that need to know the remote. For example, push and pull and fetch, and the things that actually talk between repos need to know the name of a remote. The initial remote is called origin. Again, nothing special about that name. Again, I can delete that pointer. I can send it somewhere else. It doesn't care. It's just that by default, the initial branch is called master and the initial cloned remote is called origin. But otherwise, there's nothing in the code that presumes those. It's just that it happens to be the default names. Okay, so the typical workflow is that you're changing files and committing them. Changing files, committing them, repeating that over and over again. Whenever you do a commit, you're always on some branch, like master. So a branch, though, is just really just a named commit. So in other words, when I am on the master branch, my head points at master and master points at a SHA-1, and that SHA-1 reflects the previous state of the files that are currently in the directory now that I've been making changes. When you commit, the action of a commit takes the current head and says that's now the parent commit, takes the new index and adds that together with the parent commit and the message and says this is the new commit and moves the master one step forward. So each time you're making a commit, you're basically making a chain. Every parent commit points to the previous commit, and each new commit has its own SHA-1 that reflects the current state of things. So that's basically all committing is doing. You're basically making this directed graph of every new commit being a SHA-1 consisting of the message plus the parent commits plus the tree. And that's what it's recording every time you say commit. So the branch is moving forward constantly to become the new commits. So you're basically just creating this little link. So you're creating a directed acyclic graph. Ooh, fancy words. All right. And they're rooted in the branch heads. Okay. So in other words, you might have multiple areas of development. So you might have master, and you might have feature 1, feature 2. And again, these are all just names for a particular commit that has parent commits leading to older history, eventually hopefully leading to a history that's in common when it actually branched off. So when we talk about merges in a few minutes, merges is just a commit that has multiple parents. So in other words, when I come back from multiple parallel trees, I'm going to have 2 parents now. And that's the only difference between a merge commit and the rest of the commits. So they have multiple things. So again, typical workflow, just to make this a little more concrete, edit, 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 right? Git add the files you've changed, or git add dot, whatever it takes to do that. This is going to add the files to the index. And then you say git status. Git status is cool. I say it a lot. Git status just says, here's what's going on right now. You have these files have been changed in the working directory. These files have been added to the index. And what's also nice about git status is it also tells you how to undo that if you don't want to do that. So it says, well, these files have changed and you've added it to the index, but if you don't want to do that, then type this command. So it's actually pretty helpful all the way through. Yeah.
You're using add even though it's an existing file that you didn't play with?
Yes, what you're adding is the fact that you're adding its current state. So the file's already in the index as the previous state. And if you didn't say add, it would try to commit it in its old value, not its new value. Add always says, I want this file in its current state to be the next commit. So if you fail to do that, nothing changes in the commit, even though it might be changed in the working directory. Make sense? All right. All right, so we're constantly saying, now there's a shortcut. When you say git commit, you can say git commit -a, which says all the files you already know about. Just pretend I said add to all those. What that misses, though, is if you add any new files, it won't pick those up. So I just think just type git add dot sometime is pretty handy for that. All right? Okay. So git status tells the difference between the old commit, the current index, and the working directory. Gives you a pretty voluminous way of going through all those. So we say git commit again. We're popped into a text editor. If you just want to type a one-line message, like I do a lot of the time, you can say git commit -m in a text string as a single argument, and then it just takes that message. So that avoids the whole text editor step. And sometimes when I'm working remotely, I don't want to have to fire up an Emacs or a VI remotely, so I just say the message in there. Okay, the first text line, as I said, is used for all the short logs. Anytime we're talking about a series of commits, then it just has this first line in it, which is really nice. But you can always get to the full message by typing longer commands. So again, what's happened here, as I described a moment ago, is whatever branch we're currently on, like master, then the current commit that master represents becomes the parent commit for the commit we're about to create. And we take the message and we take the current SHA-1 of the tree that's in the index, and we put those all together, and now it's a new commit. And then you're back to more editing. Okay, but what branch, right? So Git really encourages branching. It encourages going off on a diverse workflow. Because in reality, a branch is just 41 text bytes. So a branch is just a name of a file or directory and a 40-character hex string. That's all it is, so 40 plus a new line. So that's all it is. So typically what you do is you create branches anytime you want to make a change. And I know that's probably something interesting to get used to, but it's trivial for me now. It's like I said, it used to be like branch in CVS, branch it, but it has to be added. But in Git, I do it all the time. So typical workflows, I think of something I want to change. And I say git checkout -b, the branch name, topic name there, master. And what Git does is it starts with the current head that's in master, and it creates a copy of that in topic name. So now we have two branches that refer to exactly the same commit. This is how every branch starts. And also checks it out in the sense that checkout means this is also, I'm making the current working directory attached to topic name in this case. So we also have that as being my current head. And then we work, and commit to topic name. In other words, now master isn't moving, but I'm going ahead on a side branch creating new commits onto topic name. In other words, I'm adding new features, so I'll keep working until it works, right? Now I've got this new feature. And now it's time to bring things back. So it's great because then I could check out master. Now the tree, the working directory, once I do that, reflects the original point of master. Now we haven't lost the files yet because they're still in the commit for topic name, okay? So they're still over there. But now we're rewound back to master at this point. And then we say git merge topic name. Now what that says is that Git will now look at all the differences between master and topic name and merge them together. Do the same thing for both, okay? So we're going to change master, because that's the current checkout, by including the differences that make up topic name. Now in this case, topic name is a direct derivative of master, so the common ancestor between master and topic name is master. So it knows that. It says, okay, well obviously anything that's different in topic name, take it. There's not a way to have two different differences, so it just takes it all, just slides it right forward. So at this point, now that I've done this merge, master is now again the same as topic name. We've actually moved master up whatever commits were happening to make that topic happen. And then of course we say, yeah, delete the topic. Now, this is a trivial case of just creating new items until it's ready to go and then sliding master forward to reflect that. And that's often a process. What's great about that is that there could have been two different development branches happening off of there, and the right thing will still happen. We'll talk about that in a second here. So in other words, let's say that I'm really creative today and I want to try two different things. Okay, so I'm going to check out topic one. Okay, so maybe this is like making it in color instead of black and white or something, right? So I've got that, and work, commit, work, commit. Okay, so now topic one is moving off away from master by a number of commits. Everybody with me so far? So topic one now has some commits on it, right? Okay, then I go, well, I got this other brilliant idea. So we create topic two, but I don't know yet if I'm really going to finish with topic one yet, or I might not be working yet. But I want to work on this other thing now, because I'm ADD, right? Okay, so I want to go to this other side and start working on that now, right? Work, commit, work, commit. Now we have a split. So we've got the original master. I've got commits that went off in topic one's direction. And I've got commits that went off in topics two direction from master. Everybody see what's happening there? I'm horrible at drawing things, so I have to do this all just in the air. Okay, but anyways, pretend there's drawings like this. Actually, there's this great book called Pro Git by Scott Chacon, who's the same guy who who's built GitHub. And it's available for free and has great diagrams. So I wasn't going to steal them and put them in my slide presentation, but go look at the book. It's got some really good drawings. Okay, it's called ProGit. ProGit. Scott Chacon, C-H-A-C-O-N. Yeah, but it's all online. Just Google for ProGit and you'll find it. Yeah. You can actually order it too, but I don't have a hard copy of it. I just look at it online. Okay, so now at this point we have master is here, and we've got topic 1 went off this way, topic 2 went off that way. Now at this point, I'm happy with both of those, right? So I want to bring them work back together. Now, it's possible that I've changed the same files in 2 different directions as I made these 2 different topics, right? So now we have to do some math. Well, we don't do the math, Git does the math, okay? So maybe even I went back and did some more work on topic 1. So now I've got some more work done. That's what this is doing. So we need to decide how to bring them together. Because actually Git gives us the choice of 2 different ways of bringing this divergent history back together. We could merge them, and what it would look like if you graphed it is it would be like these 2 things diverging and then being brought back like this. So basically 2 different parallel paths of execution, parallel development, and then brought back into one. But Git also gives us the option, which I think is really cool, of rebasing that. Essentially playing one set of commits on top of another set of commits to make it a linear history again. So each one has its own pros and cons. The merge is probably the easiest one to understand. You basically look at files that are different and you bring them back together. In this case, let me do the merge first. It's git checkout master. So now we rewind back to the spot where we first diverged. We say merge topic 1. Now, this is a trivial merge. Actually, there's a name for this called fast forward merge. In other words, since master is a direct ancestor of topic 1, the only changes are the changes that are brought in by topic 1. So all it does is just move master immediately there. It goes, okay, I'm done. There's no way that can conflict. There's no way that can break anything. I'm just basically moving master up to topic 1 at this point. So now at the end of this command, topic 1 and master are both pointing at the commit that topic 1 finished at. With me so far? Okay, right? And again, it'll say fast forward merge. Now at this point, Git will let me delete the branch called topic 1, but keep in mind that that branch name contained the SHA-1 that represents topic 1, but that same SHA-1 is now also contained in the branch called master. So it says, hey, that's cool. You can delete that branch because I've got all that work somewhere else. It's all in the current master. Okay. If you hadn't merged that in, Git would have complained at that command. You can force it to do it, but usually that means you're doing something wrong, so don't do that. You're going to lose work if you delete a branch you haven't incorporated yet. And Git will track that for you. Okay, so delete topic 1 now. So now all I have is master, which is now where topic 1 used to be, and I still have topic 2. And it's now divergent history now. So we have different histories in different directions, okay? So now what happens is we say, we're currently checked out on master, we say merge topic 2. Now here's where the brilliance of Git comes in. It's going to look at master and topic 2 and say, okay, in order for me to compute properly the merge between the 2, I have to go back and find the common ancestor. Because again, I got to know if a file's changed 2 different ways, which of it was the original, which of it was changes from this, and which of it was changes from topic 2. So it figures out the original merge base, is what's called, the common ancestor, and it turns out it was the old master, but we don't know that. We don't care at this point. By doing this merge, then, conflicts actually may arise. For example, I may have changed lines 1 through 10 of a particular file one way in one file and a different way in the other file. Now, Git can't figure out which one's correct for the merge. It requires human intervention at this point because it's got to figure out. He can't know. It doesn't know. I may have also renamed a file in 2 different ways. It could be that I moved the file to one directory here and a different directory down here. Or I might have replaced a file with a directory in 2 different trees. And there's all sorts of ways conflicts can happen. But you need to resolve these. In other words, it's going to stop and say, merge conflict here. Here's the files I can't figure out what to do with. And for some of the files, if it's something like a text edit conflict where different parts of the files change different ways, what it'll do is it'll edit that file and put your traditional merge markers in there. Some less thans, the old name of one branch, the content for that branch, some equal signs, the name of a second branch, content for that, and some greater thans. So you might have seen this if you've used traditional things like SVN and CVS, same sort of thing. In fact, it's actually using the same old code for all that. Now you need to fix those, because if you commit that with that in there, people will hate you. Okay, so do not do that. Do not do that. I know this from personal experience. So anyway, do not do that. Okay, you need to fix that. Okay, one thing is probably not valid C syntax at that point. Okay, so you fix that. And once you fix that though, you simply resolve it all to the point where you now have, you run your test suite, make sure thing still works with everything resolved for the two different ways. And then you can say git commit dash A. This is what I was saying before. When you use git commit dash A, it's like an add. It adds everything that's currently known by Git. That's pretty much what you want. And again, you're given a chance at this point to say, well, we were merging this branch and that branch, and I had to like figure out a way to do both features in this particular file or whatever, right? Okay, so that's probably 90% of merges. Yeah, go ahead.
Yeah, so can you talk some about the branch dash, git branch dash D?
Yes.
So can you still see that if you do that, you still see, oh, I had topic 1 at some point?
Only by looking at logs. It doesn't exist in your current view. If you say git branch, which shows you all your current branches, it's gone now.
But in the logs, you can see you did it.
You see it's in the logs, yeah.
What if you don't do that dash D?
It's still topic 1, so it'll still stick around. When you do this merge, master will be updated, but topic 1's still going to be hanging out there on the side. Yeah, so it'll show up in logs, it'll show up in any kind of evaluation of what's going on. So you can leave it there for historical reasons. There's nothing wrong with, nothing that requires you to delete those. I just think after a while my workflow would be kind of noisy if I had all these branches in there that weren't referenced anymore. Question over? Yeah.
So when you have those other kinds of conflicts, such as a file that's been renamed in different ways, how does Git inform you of that?
Again, in this message, it says, I've got a directory here and a file here. I have no idea what to do with that. Or I've got a file renamed here and a file renamed. I don't know what to do with that.
Well, if you've got two files that have been changed to the same name, for example, does it alter the name so they don't conflict? It can both be there? Or?
I think it leaves both files in their original place, or because you're merging in from master topic 1. So if it's a different place, topic 1, I think it puts the file in topic 1 too. So you really just have to resolve that. Whatever git status is at this point, you've got to fix it all before you can commit. Yeah. And
what happens if you merge in a branch and then you go back and you do more commits on the branch? Can you do that and then merge it back in again?
yeah, if I didn't delete topic 1 here, for example, and I actually, oh wait, I also need to do this as well. Right. So after I've merged, and so now master is the sort of the sum of topic 1 and topic 2 plus the original master. If I made more things on topic 1, I can merge that back in.
Okay.
And the new merge base is in fact the old topic 1. So it's only the additional 3 or 4 commits I'm making on there, and it goes, well, that's my current ancestor now. So very unlikely you'll get any conflicts from topic 2 now, because now you're still already you're already at the merge of the old topic 1, the old topic 2 plus the few commits you've made on topic 1 again. Yeah, it's very flexible. That's why it's always computing the most recent ancestor, because that's your baseline that you're working from as you start doing your splits. Yeah.
When you do that, the last commit there after you've done your conflict fix, is the merge done, or do you have to do the merge commit and tell it?
No, that's done. The commit is done.
The commit knows that it had a conflict. And
yeah.
How does it know when you've done all your conflict fixing on the fact that you don't have more?
You can't lie to it. You have to, when you do that command, you're saying, I'm done. And so whatever way that is now, too bad. That's your commit for the end of that. And if you then push that and it breaks things for other people, you're going to be hated. Yes. So don't do that.
So the merge is kind of like you do the merge, that's done, and then you have to fix the conflict, and then the whole merge is officially done at that point.
Exactly. That commit says, I am done. And the merge command actually leaves behind a temp file under .git that says we have a merge conflict, so that needs to be resolved before we do anything else.
Tracking you have, and then when you do the commit of the files, it knows that.
No. When you do any commit, clears that.
Any commit clears.
Yeah. So as soon as you say commit, it says I'm done with the merge. So yeah.
Wipes out the temp files. Okay. So it doesn't know which things you had conflicts in.
Well, if you say get status, it's looking before you do a commit. If you say get status, it will tell you what it knows is broken.
Okay.
And you can add things to the index, and it slowly reduces that message.
Right.
But the moment you do a commit, it says Git presumes that you're good now. So it just gets rid of everything else. So Git status won't tell you a thing now at that point.
Status will tell you which ones you haven't fixed yet.
Yeah, constantly it tells you everything you haven't fixed yet. So you can keep looking at that iteratively until you get that all worked out, and then git commit. But git commit wipes all the information out. Yes.
Okay, cool.
So you're saying that it's probably not a good idea to do a git merge the last thing before you head home for the day, just in case it.
Yeah, unless you like to be very confused the next morning, yes. Although, there's actually a school of thought that you should, if you're doing like test-driven development, that the last thing you should do on a day is add a test that's broken. Because then you'll know the next morning what the first thing is you should be working to fix. So I like that strategy, actually. It drives work. So, but it's up to you. Over here? Yeah, think.
Yeah, I was wondering if this conflict resolution or the status that it's not resolved yet, is that tied to a particular branch or is it more global? Like, for example, if you realize we have to work out this conflict, but I want to do work on this first. Can you go to check out to some other branch and then come back to
No, you're currently in a sort of a dirty working directory situation. There's ways to stash that with git stash, and I don't remember if that saves the merge conflict information. But really, you shouldn't do this till you're ready to bring stuff together. And if you realize it's broken something, one thing you can do is you can just never commit this. And if you check out something else, everything about this is forgotten because the merge didn't work. So you don't have any update of master at this point. Master is still its old place. Okay, so master hasn't changed yet until you do that commit.
So if you recheck out master, does that return?
It resets everything, yeah. You're back, so you can just do whatever you want after that, right? That's the nice thing about Git is like there are times before you commit, everything's just in flux. Unless you've actually committed something, master hasn't moved forward. Now merge will do the commit to move master forward if everything works. But if it breaks, it just says, I'm leaving master where it is. You can look at that if you need to. You can check out this other branch, but once you check something else out, it will reset the entire working directory for you.
and the next commit just finishes off the merge?
Exactly. So it'll be one more commit on the master branch, right? All right. All right. So that's merging, which is going to happen a lot. So you're doing work, somebody else doing work, you're pulling those together. That happens a lot. Now, again, it creates a commit tree that looks like commit, 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 to splitting off things, and then eventually a merge commit back over here. Okay. Now, the other thing I like is that Git does rebasing. Rebase rewrites the commits. In other words, it's going to take the commits of topic 2, as we're about to do the rebase here, and actually apply them as deltas on top of topic 1. So it's going to lift them and move them around to actually being applied in sequence. The problem with this is that it breaks the SHA-1s. So there's a SHA-1 that represents the first change between master and topic 2. That's a SHA-1 that says, here's my deltas, here's my parentage, everything that. Now, if you take that delta of the changes to those files and you apply that up to the end of topic 1, that doesn't have the same parentage anymore. It's the parentage is the current topic 1 commit, right? So it's not going to have the same SHA-1. So this is okay if you're doing it within your own repo. But if you at some point have pushed, as we'll talk about later, the commits for topic 2 out to other people to share it with them, you've effectively broken their history. They won't be able to reconstruct this properly. They may even end up, when they do merges, with double applications of some of the patches. So this is not to be done if you've ever published anything. So this is only in the privacy of your own cubicle.
But you could work on a feature set over here, a feature set over here, and then rebase one on top of the other.
Right. Before you push it, though, you got to do it before you push it. If you ever push anything, don't do any rebase with those ever again. You have to do merges to pull them in. But because yeah, merges will properly record all the SHA-1s involved on the way down, because again, it's got parentage all the way down. So now if I push this, I already have all the commits that made that up. So this is the difference. So instead of, on that second step, instead of saying check out topic 2, git merge master. Oh wait, I'm doing it backwards. Interesting. Oh, that's because, yeah, rebasing, I'm actually affecting topic 2. Okay, so I'm checking out topic 2 this time. So this is after I've done the merge with topic 1, which was a fast forward merge. So now I have topic 1, I've deleted that. Master is now where topic 1 was, and I've got topic 2 going this other direction. So that's where we were just before this command. Okay, I check out topic 2. And the reason I'm checking out topic 2 is because I want to take that chunk of commits that represents the difference between topic 2 and the old master, and I want to replay them on top of the end of topic 1, which is now the current master. And I do it by checking out topic 2, git rebase master. So now what Git does when it sees this command is it says, okay, here's these commits on topic 2. here's this master over here. What's the common ancestor again? So it computes that automatically for me, figures out what the common ancestor is, and it takes all those commits as essentially patches. So it takes those patches and plays them on top of the end of topic 1, copying all the commit messages and the dates and times and everything directly on the end of topic 1. What you end up with is a linear history now. You have from the original master to the current master, formerly topic 1, to now the current topic 2, which is replayed patches from the old topic 2 hanging out over here in the corner. Yeah.
Are they done in the proper order so they're
Yes.
interpolated into the middle of the history of?
Well, they'll be at the end of the history.
Oh, they'll be all at the end.
They're all going to be at the
When
end.
they were originally done?
Timestamps don't matter. At this point, we're replaying all the topic 2 commits on the end of topic 1 in sequence as they are. Now, with any time we apply 2 different sets of patches to the same set of files, we could have merge conflicts. In other words, I may have the first patch of topic 2 may affect the same files that topic 1 has already changed. So when we play that on top of it, it may conflict, okay? Now, what's interesting is that it does these applications one by one. So the first thing might break. Now it tells you, I'm in the middle of a rebase, fix me, okay? And then once you fix that, you do the same thing we did before, you say get rebase -- continue. That says, okay, now try the second one, try the third one, try the fourth one. It knows all the patches, but you have to tell it to go ahead. And each one may conflict. That'd be annoying, but you may have to fix it every time. But generally, I found rebases, as long as you're not working on exactly the same area, they just play on. It's fine, yeah.
Could it basically be thought that the rebase is kind of like retroactive continuity? You're basically just pretending the commits happen later than they actually did. Right?
Yeah, and to a different base. Because, again, these commits down in topic 2 were happening to this old master back here. So you're basically playing these patches on top of the end. Right? It basically is rewriting history, yeah. Okay? So, again, we could also say in the middle of this, whoops, just start over. This was definitely not a good idea. Or I got to go home now. Or whatever, right? So get rebase -- abort. Or you can also say, well, that patch actually wasn't that important. Just skip it. So actually we'll leave it out of the sequence. So there's a lot of flexibility with this stuff. It's really kind of cool. Yeah?
So what do you use this for?
To make linear history rather than parallel history. When you're using logs, when you're looking at log and commits and stuff, it's kind of nice to have it all in sequence rather than having this bushy history to kind of deal with. For yourself, at least. I mean, once you have public commits all applying to the same thing, you probably want those as separate histories to be able to get to the same spot. But in terms of working on it itself, this is really nice. It just makes everything linear again. Makes it so I did this, then I did this, then I did this. That's a lot easier than thinking of than I did this, and at the same time I was doing that. I did this, and also at the same time I was doing that, and they're affecting files in different ways. Git log can select things like linear, or can select based on timestamp, so you can kind of get to it, but it's a little harder to do it that way. So that's why rebase is really handy. Yeah.
I have a real life.
No, sorry, you. I'm trying to put it that way.
I have a real life example that happened in Profile Read this past week where somebody forgot to rebase when they did a merge of a long sequence of stuff, and it left the rest of us in the dark because these things came in intermixed, and we couldn't see the whole effect of this one branch.
Yeah.
It was going back and looking at get log. You see parts of each branch at various times, and you can't see the total. It obscured what happened.
Got it.
In general, if you're creating your own topic branches and working on multiple things, before you merge them into master, rebase them onto master. That way it'll actually be a fast forward merge. At this point now, if I said git checkout master, git merge, so actually at this point I just say git checkout master, git delete topic 2. That would be all I would have to do there. Git branch -d topic 2, sorry.
So a rebase essentially implies a merge?
No, a merge is a merge, a rebase is a rebase, but the effect of topic 2 is now applied on the end of topic 1. Okay, yeah.
Could you summarize by saying that you merge your own changes but rebase in public?
Other way around.
Other way around.
You rebase your own changes while it's still local.
Okay.
And then you merge other people's public stuff in. You can't really rebase on that. It doesn't work very well. But, there is a case, though, where you want to you almost have there. There is a case where you want to rebase from public changes. For example, I'm tracking somebody else's master. So I'm doing my own development locally, and I've got somebody else's master that I started from. Now, I update using stuff we're going to get to in a few minutes, hopefully before we run out of time. I'm pulling in their changes, right? My changes actually haven't been published yet. I would rebase on top of master, my topic branch. So now my changes are played on top of the upstream master. So if I ever push that, it looks like a linear history for that, rather than having this bushy tree where I go sideways and back up. As long as I haven't published, I can rebase. The moment I publish, don't do that. You'll upset everybody. Okay? Yeah.
So if previous to this,
Mhm.
you hadn't done a merge, you were in checked out topic 1, you hadn't done a merge. If you do check out topic 2, then is that equivalent to then get a fast forward on topic 1?
No, it won't be anymore. Oh, wait, let me think. So I've got master, I've got topic 1. I haven't moved master forward yet. Well, if I do a check out topic 2 and get rebase master, it says you're already there. Because
what if you did a rebase topic, instead of get rebase topic 1?
Yeah, it would be the same thing as what this is doing now.
That's right, yeah.
Right, so you're basically playing on topic 1, except master's still going to be way back now. Yeah, and then if you say get merge topic 2 while you're at master, it's just going to be fast forward because it's all one line. Yeah.
Okay, so what if you're in topic 1?
Yes?
And you got that topic 2? You're in topic 1, can you merge from topic 2 into topic 1?
Yeah.
Put everything up there and then back to master.
Well, what merging back to master then will be is a fast forward because master was the common ancestor already. Yeah, that would work too. There's lots of ways to get to the same commits, but
I'm asking, they're effectively all the same thing.
Yeah.
You're pulling all your changes together and then.
Yeah, but the thing I also want to get across here is that branches are ephemeral. There's not. I mean, people always want to say, "What's the history of this branch?" I go, "Well, what does that mean? You mean what are the commits that led up to this particular commit?" Because I can tell you that with log, but there's not an entity associated with each of those commits that has the branch name in it somewhere. The commits are just commits, and they just happen to have a convenient name called a branch to be able to pull them together. And once you start thinking this way about Git, everything becomes simpler. Because, in traditional change control systems, branches have a real solid identity. But in Git, it's all ephemeral. It's all just whatever happens to be there at the time to be able to move these things around. So once you get that in your head about what the commits are doing, everything else becomes simpler. Yeah.
Have you ever been in a situation where you needed to share a branch with somebody else, but you didn't want to do that because then you couldn't rebase after that?
No, I just know that I can't rebase then.
Okay.
Yeah. And it's not bad to have merges. It just, again, it complicates the history a little bit. So once I share it with somebody, I'll then lock it down, I'll rename it or something so I know I can't, or maybe I'll merge it to my own master first and then publish that. Then I know that I can't possibly mess with that at all. Or I'll rebase it first on my master, share that, and now I'm done. Yeah. One other feature of Rebase is it allows you to rebase interactive. And this is a really cool option. Like, let's say on topic 2, I got all the way down there, but I really, like, one of the commits was sort of just a fix-up commit or whatever, and I really don't think I really want to keep it. I can say get rebase -I with the same parameters I would give get rebase, and it will pop me into a text editor that will have the log subject line of each of the commits with the word pick and the commit ID following it. Now, the word pick there means something very particular. Pick means go ahead and, when I finally commit to this, replay all of these commits. But that's a text editor, so I can actually change the order of the lines, and it will apply them in that order. I can totally delete one of the lines, and it will not apply that particular patch. Like maybe I only want some of the features over in this other branch. I can also say merge, and it will take that commit and merge it with the previous commit as it's replaying it. So for example, let's say I've got 7 commits, and it's too messy. It's like I was working around trying to get something, finally I got the right solution. I could say pick, then merge, 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 merge. And it will collapse all of those particular commits into one commit in the final branch. So very, very nice. Get rebase -I is very, very cool. Okay, enough on that because we've got to keep moving here. Okay, so, yeah?
You have to have a fairly modern version of Git. It's buggy.
Like in the last 4 years, maybe? Yeah.
No, I do a lot of that, and I ended up backing up, copying my work versions because that would end up everything would be all screwed up.
Interesting. I haven't had that problem happen yet, but maybe I'm not doing the same thing you're doing.
Anyway, so
yeah.
All I did, I thought I couldn't tell since I don't know Git very well, whether it was me or them.
Okay.
But when I upgraded to a later version of Git within the last 6 months,
yeah,
I no longer have to do that.
Okay.
Turns
Okay.
out it had to have been them.
Okay. Okay.
So anyway, I've forgotten what numbers.
Okay. Well, I believe you, but I never had that happen to me. Yes. Okay. Anyway, so when you're rebased again, as we said, the merge is a fast forward, and then we would check out master and get merge topic 2, and then I try to delete topic 2. That's sort of what I said at the top of the slide there. There goes my throat, and you'll be eventually here. Okay, so get log is going to show me the changes. Okay. Get log is just going to be the summary line, so it's just going to be the one topic line, the date and time, and parentage as we go down. Get log-p is kind of cool because it actually prints the patches. In other words, the delta between the old and new versions. Of course, I can get voluminous if it's a large change and whatever. So like that. There's a lot of options to get log. Get log has like 70 different options, but so I'm not going to go through all of them. But one of my other favorite ones is --stat. And that summarizes the changes with a diff stat. In other words, it's going to show this file had 20 lines added, 3 lines removed. This file was brand new. This file is completely deleted. So it sort of shows the summary between the two of them. That's kind of convenient for reading stuff. You can also narrow the log down to just the patches that affect particular files. So for example, if you're looking at the Perl Git archive, but you only want to know where doc changes are made, you would say git log --pod, because it's all inside the pod directory. So it would only show you the changes that make documentation changes. And I do that from time to time. I pull down the current Perl archive, which is in Git, by the way, which is why it makes it relevant here. And then I say git log --pod just to see what they've changed in the documentation, which is really the only part I care about the current Perl repo. Okay, so it shows changes only for the listed files or the subdirectories. Okay, so git diff is pretty handy. Git diff by itself with no switches shows the difference between the index. Remember, the index is what's next to be committed, and the working tree. So this is the stuff that you've changed, but you haven't told Git about yet. You haven't told them these things are different there. So these are the things you should add with git add. Git commit -a would also make this list empty. Okay. Git diff and head, or any commit there, by the way, will show the difference between head, the previous commit, and the current working tree. I type this one a lot because it's sort of like this is the work product. This is the next thing I'm really going to be committing, barring any issues with index. So this is kind of a nice one. Again, git commit -a will make this empty. The third one, which I rarely use, but it's there, is git diff -- cached. And that's the difference between head and index. It's basically everything I added with git add. And again, git commit is going to make that empty. You can do git diffs with other things, though. You can say git diff other branch. So that's going to show the difference between the other branch, like topic 1, and the working tree. Or you can say, what's the difference between these two branches? So it'll show the diff between the two of those. By the way, these diffs are typically the unidifs, so it has pluses and minuses to show you the lines that are added and deleted between two different files. Okay. You can also say, this is sort of interesting, the 3 dots there, sorry, I don't know if it comes on the screen. Yeah, 3 dots. That's the differences between branch 2 and its common ancestor with branch 1. So let's go back to that topic 1, topic 2 example. If I call this and I say topic 1, topic 2, it's going to be the differences only from topic 2 back to that common ancestor, only the stuff down here. It's not going to include anything about topic 1. It's just using topic 1 to figure out where the common ancestor was. So that's kind of nice. It's basically, what does topic 2 contribute to the changes since the last time I forked that way? 3 dots. 3 dots deliberately, yeah. 2 dots would actually be the same as the previous one. So we had to have a special notation for this, which is the common ancestor between branch 1 and branch 2, and then relative to branch 2. Yeah. There's also git diff -stat, so it shows the pluses and minuses, as like I did before. Nice summary of the changes. You can also get dir stat, which summarizes the directory changes, which is kind of cool. So I use this sometimes when I want to see, okay, here's a commit on the Perl tree. What really got changed in this commit, or what got changed in these series of commits. That sort of says, well, pod had a few things changed, and lib had a few things changed, and so on. So you can see kind of the relative directories and how much got changed there. So the word tree appears a lot in the documentation, and what it means is referring to some sort of file set determined by these arguments. So the easiest way to talk about a tree item is it's a SHA-1. So if you have an absolute SHA-1 and you want to say, I want to check this out, or I want to take the diff between this and the current directory, you can just give it to it. What's nice is you can abbreviate those. Most of the commands actually show only the first 6 or 7 characters of the SHA-1. And that's because that's generally enough characters to be unique within your Git repo. In fact, if you only have like one SHA-1 in your entire repo that starts with A, you can just say the letter A. It'll just work. Okay, that's not likely. After the first few commits, probably have more than one A. You know, something, a hex character that starts with A. You only need about 6 or 7 though. And in the entire Linux repo, the current repo with the 2.6 and 3.0 kernel in it, I think you only need 5 characters to be completely unique. So you have a lot of commits. You know, that's the first 5 hex characters, right? It'll actually tell you though, if you spell out 4 of them and they're not unique, it'll say that's not unique, command aborted. So you have to like spell more out than that. But typically 5 or 6 is probably is plenty. You can also use some reserved names like the head that always means the current checkout, some branch name, a tag name, some origin name. Let me talk about that for a second. So again, when I clone a repo from somewhere else, I get a remote called origin. So I can say git diff origin / master ... master. And that's going to show me all the differences from the remote master to my current master, so I can see what work I've done locally. Or you can go the other way too. There's also, you can follow any of those with @ and some historical thing, where historical could be something like literally the word yesterday, or a date, or a version number like 1, 2, 3, 4. So it shows you the previous versions of that ref. So for example, I could say, show me the diff of where the head used to be, head at _1, ... head. And that'll show me where the head used to be versus where the head is now, and give me the difference between the two. There's a special one of those called upstream. So if I'm cloning from a repo, and now I've brought down origin / master as my master, then I can say git diff or master at upstream, which will turn into origin / master because it knows that those two are tied together. Okay, now any of the things I just had on the previous slide, you can also update with parents. You can also say, give me the parents of those. So for example, I can say _1, and that's the first parent of an item. And that defaults to 1, by the way. It's just up arrow is the same as _1. Now I'd use this, for example, to say head up arrow, which will be the head's parent. So it's the previous commit before the current commit. And typically, though, a commit only has one parent. The only time you'd have more than one parent is if it was a merge commit. So you'd use up arrow 2 to get to the second one of those. More often what I use instead is tilde. So tilde1 is the first parent. Tilde2 is the first parent of the first parent. Tilde3 is the first parent of the first parent of the first parent. In other words, 3 commits ago on a typical linear chain. This again is why it's handy to have, instead of merge matching, to actually do rebasing, because then all you have is ever its first parents. So you can use things like tilde3, tilde4, tilde5 to get back to the previous commits. So we'll see some more examples of this as we get forward in a few slides here. Okay.
So how is tilde3 different than up arrow 3?
Up arrow 3 would be the third parent of the current commit. But most commits only have one parent, so that's not going to happen. Tilde3 is the first parent of the first parent of the first parent, essentially the linear history. I've never used tilde in practical terms. Let me just say it that way. I've never used up arrow in practical terms, but I've used tilde all the time, though. You know, like take the last 5 commits on the current master branch, and I want to see what they did. Git diff head tilde5 ... head. Okay, that sort of thing, right? And on some operations, you can actually pick files out of these commits. Nothing of what we've seen so far, but you can actually say colon and a path, and it actually picks out the blob for something. There's a command called show, git show, where you can say git show head colon and a path to a file name, and it outputs on standard out the actual contents of that file. Occasionally handy for doing things. So here, here's some examples. Git diff head first parent to head. That's going to be the most recent change in the current branch. I could have instead written that. I more typically write that as head tilde. Okay. Git diff head 3. That's the last 3 changes, right? What damage do they do, and so on. All right. Now there's a few cool commands that come with the current Git distribution. One of them is a TK-based display. So you can see kind of a graphic display of paths going up and stuff. I'm not going to bring that up right now because it'd be hard to put on the screen like this. So it's going to be sort of a history of everything from my topic and origin back to their common ancestor. Okay. You can actually say get K, get DK. I don't know how to pronounce this. Get, you don't have to say it. We just type it. Get K all, and that shows all of the branches that you currently have active all the way back to the common ancestor. So it shows everything. You can also say just show me this range of commits and so on. There's also show branch, which you can actually type in a command line, which doesn't invoke a TK widget, just simply does a sort of a command line view of all those commits as well. Okay. So again, we talked a couple times about git clone. So what git clone is doing is it's going to copy somebody else's repo using a remote spec, which I just realized I don't have a slide for, but remote spec would be things like either a directory name, like you're copying in two different places on the current file tree, or maybe it's a HTTP spec, or a git colon spec, or a git SSH colon spec. All these things you've probably seen before, perhaps you've played git before. So when I clone, though, I'm bringing down all of their local branches to be my remote branches. And again, when you clone, it's called origin. So origin/master would be their master branch brought down as my local origin/master branch. Or if they have a topic 1 branch when I clone, then there's going to be an origin/topic 1 branch on my area as well. You don't want to do development on top of that. What you want to do is check out a local branch that builds on top of a remote branch. So for example, I might say git fetch origin, which now says, once I've already cloned, git fetch origin says, go out to the current thing that I know as origin and pull down all the current branches that are there. So that's going to load me up with that. But that hasn't changed my working directory. That hasn't changed my local branches at all. So if I have something called master and there's an origin/master, they're probably different now. They're probably a different space. So, and that's probably the next step to do. So I've done some local work. The other guys have probably done some local work. Now it's time to kind of resync again. That's what we're about to try. So what you do is you take, typically you'll want to rebase your changes on top of the upstream. So I have current master checked out. I say git fetch origin, that's going to pull all the stuff from remote, and then I say git rebase origin/master. So let's see how this is looking graphically here. So I've got a master that was originally the same as origin master because I cloned the remote repo. Now I'm going to do some more work. Okay, so I'm off in this direction. They're probably going to do some work, so that's off in a different direction. So now we have master here. We have origin/master down here. The fetch pulled that in and moved this path to here. Okay, so what this rebase is doing is it's saying, okay, find the common ancestor, which was the old master back here, and take the changes that are currently checked out, in this case master, and replay them on top of origin master. So now we've got linear history again, but I'm now currently on top of the work that's happening upstream. Yeah?
Will you do this in different directories or one plain directory?
No, you just it's the one git worker, yeah. Does that make sense?
Makes sense. I'll talk to you later.
Okay, all right. All right, so I now have the new master is now moved up and I'm upstream, I'm lined up on upstream. Of course, somebody may have, changed things in ways that conflict with me. So like any rebase, it's going to stop where it breaks. I have to fix it and move it forward, get rebase continue until I'm all the way done. Now, if I've pushed master upstream though, somehow, I don't want to do this. I want to just merge in master instead. So I'll say git merge origin master. So I'll make kind of a bushy tree, but at least now I can play well with others. You can also do fetch and rebase in one step. You can say git pull. Pull in git is either a merge or a rebase, depending on the absence or presence of the rebase switch. So unlike other change control systems where you pull to update, in general you only pull in git, excuse me, if you want to do this merge. Otherwise, you typically want to use a rebase for that. Okay. Now, if you have permission, you can then also push upstream with push. By default, that defaults to the origin repo, and it will try to move my master, whatever my current master commit is, up to the repo, pushing its master forward. Now, there's a couple things with that kind of a push. If I've done this rebase or merge, then my master includes their master already. Somehow my master has as a history element their master, which means if I push right now, it's going to be adding more commits without losing anything. Okay, so because I've already included their master in my code, so therefore it's not going to hurt if I push it. But it might be that in the meanwhile, between doing that get poll dash dash rebase, or maybe the get fetch origin, get rebase origin master, or maybe a merge, whatever you want to do there to make it locally synced, someone else may have pushed to master. Okay, now what's going to happen there is if I try to push that, I would effectively be losing the new commits that are up there. So most repos are configured in such a way that it allows fast forward only, which if we recall the term from a little bit a while ago, that means that it'll only work if it's just adding commits, and it will abort otherwise. So if I'm working with a typical GitHub repo or something, and I try to do a push and it says, sorry, not a fast forward merge, that's what it's talking about. It's saying in the meanwhile, between me trying to sync up my local repo and the remote repo, somebody else also beat me to it. Somebody else already pushed some more stuff. And all you do is just repeat the cycle. You just basically pull it down again, sync it up again, and then you can finally push. You have to do it quicker this next time, that's all. Yeah, it's a race at that point. So this is the one area where having distributed control systems is a little more complicated because everybody can be updating the master on top of everybody else, but you just have to get there fast, yeah.
If the upstream is not configured that way, is there a way you can say at your end that says push only fast forward and fail otherwise?
I believe so. I've only been working with repos that are sanely configured, so I've never seen that.
What's the syntax for it?
I don't know. That's what I'm saying. I'd have to go look it up. Man get push, yeah. Okay, so sometimes you want to throw work away because things are crazy or whatever. So get reset dash dash soft makes all the files. So I've got a current commit. I've made some changes. I've done git add with those. And I say, well, I didn't want to add all those files. I only want to add like 3 or 4 files and make a commit with that. Get reset soft does that. Get reset dash dash hard is pretty bad. It makes the working directory looking like the last commit. In other words, I've made some changes and now I'm just saying, oh, what was I thinking? Okay. So get reset dash dash hard actually resets the working directory. Don't do this. It makes you can lose stuff that way, right?
Isn't that effectively a new checkout?
Yeah, it's the same as checkout, get checkout dots, but this just works this way. All right, get reset dash hard 3 commits ago. Well, that's really bad, right? So that's throwing away the last 3 bits of commits that you might have made. I do this occasionally, when I want to throw away the word. Now, there's an interesting thing though. If you've already pushed that, you've already shared those commits with other people, this is going to be bad for them because now if you build more things on top of your previous commit, they've got these other commits hanging out there and it's no longer going to be a fast forward merge for them. So there is a way called git revert where you can make a single commit that undoes the working directory to whatever the commit is that you name. So for example, you git revert head ~3, we'll add one more commit that effectively undoes the previous 3 commits. So that's what you want to do if you've already pushed this stuff though. But typically, if you're throwing stuff away, you probably didn't want it in public in the first place. Okay, too bad if you did. All right, you can also check out a particular file. So you say git checkout head and a file. This is great if you screwed up, deleted a file, and you really want it back again. So you say get it from there. And this is also nice if you want to check out a version from an older commit or a different branch, and you want to bring that into the current tree. This would be the way to do that. Okay, as I said earlier, git ignore can define things that you want to ignore. Typically it's patterns like star.c, star.o, but you can also put a not in front of there. So you can say, for example, star.c to ignore all the C files, but not foo.c, because foo.c is special. So you want to track foo.c, but you don't want to track the rest. Any line that doesn't have a slash in it is checked against the base name of the file, otherwise it's a shell glob. And you can also anchor that with a slash at the beginning to be in the current directory, otherwise it applies to all directories. Now, the git ignore can be checked into the repository and tracked just like all the other files. And typically you will. You'll put a git ignore that makes sense for everybody that has to use this particular repo. Okay, but you can also have in your current checkout, in your current repo, you could update and edit the file git info exclude, and that's going to be that's only going to apply to you. That's never going to be checked in with a repo. It's not going to be cloned. It's just for you. So that's typically where you'd put things that are related to the way you're particularly processing files, like maybe my Emacs star tilde thing or whatever, right? And both of those can work together. The thing that's important is a git info exclude will not be cloned. Okay, I've got, what, 15 minutes? Is that right? Okay. I've got 8 more slides, so here we go. All right. So commands are affected by configuration a lot. So there's command line options for a lot of things, but there's also some things that Git stores in a config file. So Git config gives with a name, gives it a value, sets name to value. The name can contain period for some sub-items, and Git config name fetches the current value. You also say Git config -- global fetch or set, and that actually edits your local home directory .git config. And that applies to all the Git repos that you're using. So for example, typically what I'll put in there is my username and my email address. So Git wants to know what username and email address it's going to assign to every commit. I get it from my .git config file, my home directory. Now, there are times when you want to say, I got to go work on this branch because the boss says I got to go work on it, but I'm sort of working with something already. I've already got something in my current working directory and I'm about to make a commit and stuff, but I'm interrupted. So what a stash does is it takes the current index and the current working directory and puts those into a special place to be able to pull back later. So you say git stash and everything's just snapshotted. And then you can go out, check out other files, other directories, see what you want to do, make commits there, doesn't matter. But then you just say git stash pop and it pulls back whatever was previously there. So there are other uses for it as well, but again, I don't quite have time. I want to get all the way through the rest of the slides. You can have multiple stashes, so you can be really confused and have multiple snapshots of things you're working on. If you get to that point, though, I don't know, keep a notebook or something. I mean, it's just going to be really complex. You can name them as well, so there it is. But I also want to talk about some other things that are in Git, just to kind of give a summary of everything else that's around there. You don't have to check out a commit just to create a tarball for it. You just say git archive and the name of the commit, and out on standard out comes a tarball. So this is great. So it doesn't have to be the current checkout or anything. In fact, you can even have, no, I won't get into that. All right. It's just, not with only 15 minutes left. All right. Git bisect. This is really handy. So you've made a bunch of commits, and somewhere down here, the build is broken because, something changed between here and here. I know the build worked here, and there's like 17 commits. Now the build's broken. I'll go, well, what broke it? Okay, which particular commit broke it, right? So what you do is you say git bisect, you say the bad one and the good one, and it looks at all the changes those commits made. And it computes a midpoint based on the number of lines changed in each commit. So it's not just halfway. It kind of looks at which ones made the most changes and bisects that. And it checks that out and says, okay, now you're at this commit. So you try it and you say, did that work or not? Oh, that one's broken too. So you say git bisect bad, and it says, oh, okay, so now it's somewhere in here that the good one and bad one changed, right? So it does that same thing. It says how many lines are changed here. It tells you another commit. It says you've got about 3 bisects left. And so it tells you all the time how many more you're going to have to do. And this is great. So I'm building GNU Emacs every morning on my OS X laptop. So I pull down the Git archive of that, and they break sometimes. And so I get to use bisect for a little while, building Emacs, which takes about 20 minutes. But I get to try and see which one actually broke it. And I can say, this commit right here, this is a bad commit. It's really handy for that. Doesn't always work. Sometimes sometimes it's not just one thing that broke the build or it's whatever, but it's pretty handy. It's kind of fun. Okay, git cherry pick. As we had those 2 branches before, sometimes you want this one commit here to be applied down to the end of that. So cherry pick just takes that one. If you need more than one, you use git rebase with -i, and it's much more flexible. Git MV renames a file, as I was talking about earlier. It renames a file, but it also does remove this old file from the index, add this new file to the index. Same with git rm. Again, you don't need to use these commands. Just use normal text editing commands, normal Unix commands, and it will just work, but you need to also then do the right add commands on top of that. We talked about git push. We talked about git revert. One other handy one is git blame. Okay, so I'm looking at a source file, and I want to know which particular commit added these 3 lines, which obviously broke everything. Okay, so by using git blame on there, it goes back through all the history of that file and annotates the lines in front with the first commit the most recent commit that affected that line. So it's kind of nice for seeing who actually broke stuff. Okay, so just in terms of some general stuff about Git, you should always commit small logical steps. I try to commit things that I think people might want to leave out or select in. So in other words, the sort of logical step that represented for Git. So ideally, you want to commit every time it would pass the test suite again. Because again, if we talk about git bisect a few minutes ago, you want to make sure every commit still doesn't break the build. because otherwise Git bisect is useless. If the rule's broken somewhere in the middle, then bisect will say, well, that's bad, so you'll end up on the wrong side of the bisect. There's actually there's actually some discussion on the Git mailing list right now that I helped kick into play, where you'll be able to say in a commit, I know this breaks the bisect. So if bisect ever sees this, it knows it's one to skip automatically. But they haven't worked on that yet. It hasn't been incorporated yet. I think they're waiting for a commit from me. All right. All right. Yeah. Patches, welcome. All right. Oh, by the way, the Git project is sort of weird. The maintainer of Git, Junio, which we've interviewed on Floss Weekly, Junio does not want to pull a Git request from somewhere else. He just wants patches in the mailing list. That's entirely how it's all done. So here's Git, which is this great distributed tool. And the way you change things in the Git project is you post a patch to the mailing list. It seems ironic, doesn't it? All right, anyway, that's just crazy. All right.
He doesn't believe in his own stuff. It's the message.
Well, not really, because getting it from the list is one of the features of the program.
It's true. Yeah, it is. In fact, yeah, Git is designed to be able to do that. So that's part of it. Also, he manages it by having a mail folder of all the possible commits, and then he applies that locally. So it's also good because it gets discussion right away. So somebody posts patches, somebody else can immediately say, I applied these, and really you should fix it this way. So it sort of immediately involves other people about being able to update it. So there's an advantage to it, actually. It's just a little weird. It's like, here's this project where, you can pull from other repos and we just patches around. All right. It's easier to squash commits later than it is to break them up. And actually I said before, we can use squash, omit, reorder with git rebase-i. Okay. So we've seen two different tools to be able to pick things from other things. There's merge. Merge, of course, is bringing in all the commits. Cherry pick is bringing in just one. Let's see here. So merge is great when you want to take all of topic 1 and put it on top of topic 2 or merge it in with topic 2. Cherry pick is great when you want to just pick out 1 or 2 of the changes from topic 1 and pull them over to topic 2. So in terms of workflow, again, stepping back a little bit further, Git's workflow is really sort of fun. It's sort of a good model for how you can use Git in your organization. There's 4 branches. There's maint, which is just the maintenance release branch. That's sort of like where if there's something really broken in a past release, that's where that'll go. There's master, and that's the one I said you can build every day and it works. So they do a pretty good job of making sure that that's not going to break anything. Next is sort of, throwing some features in there. Might not work everywhere yet. Please let us know if it breaks something for you. So it's a little dicey. I don't compile next because I don't want to spend more time on this than I need to. So I'm just compiling master every day. But master does change every day, so it's kind of cool that way. And then there's PU. I don't know what that stands for. Maybe it's PU, literally. I don't know. Experimental features. So there'll be things under PU. So it'll be a PU/topic name, PU/topic 2, PU/topic 3. And so there'll be all sorts of things that people are working on. And this is sort of where the patches that are picked up from the mailing list immediately become a PU branch. And so that, if you pull down the next day's release, you can see that. You can actually start applying it, see if it works for you, and give feedback to the mailing list and so on. That's where those go. Oh, cool. All right. Each one of those is sent to the one above, so every one of these branches contains all the branches listed prior to that. And so what happens is that, for example, what Junio will do is he'll commit something to master, and then he'll immediately merge that down through next and all the PU branches, so that way every branch all contains everything that's above it. Yeah, just like I said here. All right. And so again, most features are going to require several iterations. I've made this clear before. So you commit to these to a topic branch while you're doing the design. So in other words, I have a logical idea, I want to implement it, I'm going to create a branch for it right away. And I'm going to commit along that branch. That way, if I don't finish it, but I need to start working on something else, I can branch off master again and go a different direction. Okay? It's easier to rehack this or abandon it. Like I might be trying a new feature and I just go, oh, this isn't working out. Git branch-d with a capital D that says, I know I haven't merged it to master yet. Go ahead and delete it, make my work go away. Okay? And then you fork the topic from the oldest main branch. You can refresh if you need to. Don't do that routinely because it makes the tree really bushy. And then you rebase the topic branch if it's forked from the wrong branch. And what's great is that you don't have to read all this. It's all written down on one of the man pages that comes with Git. Okay? So the way the workflow works for the Git project is they merge from the base branch up to the topic branch. So we want to find out if the topic branch actually works on top of the base branch. So we want to know if topic can be brought into master. The best way to do this is you merge the other direction, but you merge it onto a new throwaway branch. So in other words, I'll say get checkout dash throwaway topic 1. So now I'm on a throwaway branch, but it's the same as topic 1. Then I say get merge master. So that's going to bring in all the code from master and merge it in with this throwaway branch. So the throwaway branch at this point is effectively all of master as it's progressed, plus all of topic 1. Then I go ahead and test that and make sure it all works. So I run it through my continuous integration or whatever I want to do with that. And that branch is never merged in, it's just for testing. You can also publish it, but typically you don't want to. And if the integration fails, then we go back to topic 1, we add the patches to make it work again, and then we cherry pick those back onto the test branch. But ultimately, what we're trying to do is get to the point where topic 1, when merged into master, still works. And that's why we have this throwaway branch for us. We want to see if everything all plays together. Once we get topic 1 to where it works, we go back to the stuff I showed you a lot earlier, which is that we rebase topic 1 on top of master, or we'd do a merge, depending on whether we wanted a bushy history or a linear history. That's basically how that works. Just about on time. Look at that. There's further info. There's Git in Wikipedia. There's the Git homepage, the Git wiki, the Pro Git book. Here's the URL. You don't have to actually even Google for it. Look at that. Put it right there. You can get on the mailing list. There's really helpful people there. It's a very active mailing list, though, so unless you want, there's 70 pieces of email a day, I wouldn't join it, okay? Or keep it in a way that separates it out. And on there, you can also submit bugs, patches, ideas. The Git IRC channel is really awesome. Lots of people there 24/7, answering questions for all sorts of levels of things. I'm there occasionally, helping to answer out, and that's all there is. Any questions now? I've got a couple more minutes to go, so any questions?
Your slides, are they going to be these slides?
These slides already, published them on SlideShare back in January, because I haven't changed them since then. I did this very same thing. If you missed anything of what I said this morning, you can either watch it on the the YAPC channel, but I did this very same presentation about 3 months ago, and it's on Vimeo. So if you Google for Randal Schwartz Git, it's going to be like the second or third hit. This is actually a longer version of something I did 6 years ago, I think, as a Google Tech Talk. So that was sort of the thing. Linus went in to Google, and he did a tech talk for about an hour of how SVN sucks and how CVS sucks. But he didn't really talk about Git. And so I had an opportunity, because I had friends at Google. I said, can I come in and do the actual talk that he should have done? And they said, yeah. So I got his talk and my talk are the 2 talks that Google has about this. But I beefed it up by double size, and that's what you can see in the Vimeo thing from January.
Can you work on 2 branches at the same time?
Yes.
Next is like you're doing web development. You want to see your old version and you want to see your new version at the same time.
There's a couple ways to do that. One is if you're not actually editing the old version, then use Git archive to pull it out to a separate file tree. That's quick and doesn't require any changes. There is a way, there's Git workdir or something like that, where you can say, check this out, but to a separate workdir. So, but if you're not actually doing development on the old branch, I would just choose a Git archive and just pull it out and then untar that. Yeah. Okay. Any questions? Yeah.
Say you want to share your topic 1, so I'm going into the I'm looking at it, and when you're done, you go and talk about, so you delete yours, goes to the master. Now, I've still got this tracking branch, right? There's plenty of you still. Yours is gone because you deleted your topic and it's been merged in. Is there something that I would do other than just deleting to manage so there's no tracking?
Git fetch has optional switches that say make my tracking branches exactly equal to all the existing topic branches from the remote repo. So in other words, I would have my local repo and then probably something on GitHub where I'm pushing to. I would, if I don't explicitly delete the branch up there, it's going to stay there forever anyway. But if I explicitly delete it with an appropriate kind of push to delete the remote branch, it's gone from there. But when you keep fetching, you're not going to notice that unless you also add the switches to fetch to say, and also synchronize these, as in delete branches that aren't there. But yeah, there is an option for that. Yeah. I don't know the syntax off the top of my head, but every time I need it, I just go to the man page. Right. Any other questions? Was this useful? People like what you heard? All right. Thank you. Thank you.